Good morning, everyone. Welcome to the 2020 GTMI Annual Distinguished Lecture. This year, we are very pleased to feature Dr. Carmelo, President of Solvay Composite Materials. Dr. Faro will present Composite Materials, the growing pains of a young technology destined for a very bright future. My name is Ph.D, GTMI Strategic Partners Officer. To ensure a seamless presentation experience today, audience members are muted during the presentation. However, we encourage all audience members to submit any questions you have for the speaker as they arise using the Q&A panel on your screen. We will address all questions that have been submitted via the Q&A panel at the end of the presentation today. I will now turn the microphone over to GTMI's Executive Director, Dr. Ben Wang.
Thank you, Paige. Good morning, everyone. I am the director of Georgia Tech Manufacturing Institute, or GTMI. We hold many events throughout the year, some weekly, some monthly, and some others are scheduled on demand. Today's event is very unique in that we do it only once a year. Okay, so this is the GTMI Annual Distinguished Lecture event. Before I introduce today's speaker, let me just take a minute to recognize the speakers from the previous years. Okay. So we started the Distinguished Lecture in 2013, and that was the first one. Our speaker was the former CEO and the president of Ford Motor Company's Alamo Lally. The year after that, we had Dr. Reinhold Ahad, who was the CTO of a very large German company, ThyssenKrupp. Then in the year after that, we had the executive vice president for global supply chain and consumables of Walmart, the Michelle Glogler. Then we have Dr. Jeff Wilcox, the VP for engineering from Lockheed Martin Corporations. And after Jeff Wilcox, we had Mr. Dean Kamen. Many of you have heard Dean's name before, and he is known for his inventions of Segway. Okay. Last year, we had the CEO and the general manager of Global Foundries, Tom Caulfield, as our distinguished lecture speaker. Okay, so it is my pleasure and honor to introduce this year's GTMI Distinguished Lecture Speaker, who is a great business leader, an accomplished scientist, and a dear friend, Dr. Carmelo. Dr. Faro is the president of Solvay Composite Materials, a technology and innovation leader that provides advanced composite materials and adhesives to aerospace, defense, energy, and automotive markets. And Carmelo was appointed to the current position as the president of Solvay Composite Materials in February 2017. He joined the business in 1999, and prior to his current position, he served as the EVP, Industrial Business Line and Strategy for Solvay Composite Materials. In 2015, he was the CTO of Cytec Industries. At the time, the company was acquired by Solvay. He also served as a VP of Technology for Cytec Aerospace Materials from 2010 to 2014, and the Product Development Director from 2005 to 2010. Early in his career, Carmelo had leadership roles in R&D engineering and operational improvement, and was instrumental in introducing novel advanced materials and processes on multiple aerospace, defense, and automotive programs. He holds 9 international patents and has authored several technical papers. He serves on the board of governors of the Aerospace Industry Association. As you know, it's a very powerful the association, and very active nationally and particularly in Washington, D.C. And he is also on the board of directors of JEC. So LaFaro holds a doctorate of science in material science and a master in mechanical engineering from Catania University in Italy, and an MBA from Arizona State University. So please join me in welcoming Dr. Carmelo LaFaro.
Thank you very much, Ben, for the introduction, and good morning, everyone. I am extremely honored and humbled to be here. When I was listening to Ben talking about the previous speakers, as a very, very impressive list, particularly Al Mulally, who, on top of being in charge of Ford, was also the president of Boeing Commercial Aircraft, and an industry leader that I really, really admire. Really good to be here. Sorry I couldn't be there in person given the pandemic, but still very excited. So today I will talk to you about composites. And I am talking about composites as a young technology. So when I entered college in 1993, and for the first 3 years of college, I actually didn't know what a composite material was. Composite materials weren't really at the center of academic education back then. I started to learn about them in my last 2 years, and fast forward to today, I have spent all my career in composites. I have developed a true love affair with this technology. And the reason for that is that this technology has an enormous potential. And every day I've been in this business and in the industry, I've been very excited about that potential. I've always looked at what composites can do for us in the future to benefit humanity. So my hope today is to share my passion with you, and also to get you excited about the science and technology of composites. So talking about science and technology, let me talk a little bit about Solvay, the company I work for. So Solvay is 157 years old, and was founded in 1863 by a chemist called Ernst Solvay, who patented a process for the production of salt. Now, a picture is worth 1,000 words, and this picture that you might have seen before is the picture of the Solvay conference of 19. So Ernst Solvay, the founder of our company, as he started to profit from his business, invested a lot of his personal wealth and time in science and technology. And specifically, he was the organizer of the Solvay Physics Conference. And that's a very impressive picture from 1911, where you can recognize the giant of the last century. Now, probably the most common face there is Albert Einstein, who is on the right of that picture. But you also have other extremely important scientists: Lorentz, Poincaré, Rutherford, Max Planck, Marie Curie, and others. So Solvay has had a very long history, and from the very beginning, a clear passion and appreciation for science and technology. So today, Solvay has about 10 billion euros of sales. We have 24,000 teammates, and we invest a significant amount of our revenue in materials R&I, research and innovation. Very importantly, more than 50% of our products are sustainable solution. So, and sustainability is clearly a big part of the ethos of the company and what the family shareholders still have a big presence in our shareholders' basis want us to achieve. So I've spoken about sustainability, I've spoken about advanced materials. Let me now talk about composites. So what are composites? Composites are materials that are composed by two or more constituents that have very different properties, physical or chemical properties. And when these materials are put together, they work in a synergistic way. They remain separate and distinct within the structure. So that's different than, for example, alloys or mixtures, but they are able to work in synergy. Now, you can see a lot of composites in nature. So evolution has allowed us the development of structures that are composites. Wood is a composite, is made by lignin and cellulose. Our bones are a composite. They are made by hydroxyapatite, that is more commonly known as calcium phosphate, and collagen, that is a protein that keeps them together, and so on and so forth. Some examples of engineered composites, man-made composites that you see are reinforced concrete, obviously a composite. And then you have different numbers of materials, with a ceramic matrix, a metal matrix, ultimately fiber reinforced plastics. That is what we'll talk about in today's talk. So the title of today's talk is a young technology. So let's talk a little bit about history. And I want to compare and contrast the history of metals, very commonly used material, to composites. Now, if you look at metals, metals in a form not too different from the form we see today have been around since the Copper Age. Copper pendant was found in what is now northern Iraq in 8700 before Christ, 10,000 years ago. Metals, of course, evolved through the Industrial Revolution with steel, aluminum, and ultimately titanium, that is lightweight metal in the 50s. Now, composites have a different story. Technically, people use composites also many years ago. In ancient history, people used bricks made of straw, so fibers, and mud as a matrix to make bricks. In 3400 before Christ, Mesopotamians made some kind of plywood by gluing wood together. However, when we think to the modern version of composites as fiber reinforced plastics, this is a technology that is in its infancy. So we started having glass fibers in the 50s and carbon fibers in the late 60s. So compared to metal, composites it's a very young technology that has a lot of potential. So let me talk about composites as in fiber reinforced plastics today and compare them to metal. Clearly, composites continue to replace metals in multiple applications. Why is that? There are some very obvious reasons. I would tell you these are the traditional reasons composites are replacing metal. The first one is the one almost everybody is familiar with. Composites have a very high specific strength, so that's the strength to weight ratio, and the stiffness. Now, just to give you some figures, Carbon fiber composites are 25% the weight of steel, 70% the weight of aluminum, and they have 4 to 6 times higher specific strength than these two metals. So that allows people to make lightweight structures. Another advantage is no corrosion. Metals corrode a lot, and the ability to be dimensionally stable. That allows composites to withstand very tough environment. Fatigue. Composites do not have a fatigue problem. I pasted a picture here of a pretty infamous aerospace incident. So this is a Aloha Flight 243 in 1988. This was a 737-200 plane with a metal fuselage that suffered an explosive decompression at 24,000 feet over the Hawaii Islands. Now, the investigation uncovered that this was caused by some human error in maintenance, but ultimately, the reason that fuselage failed was due to corrosion of the aluminum, the multiple fatigue cracking of the fuselage lap joints. So clearly, a major drawback of metal is the high sensitivity to fatigue and corrosion. Last but not least, design flexibility. And we'll talk about this a little bit later, because I do believe that's still something that is not fully exploited. But with composites, you can make very complex structures. As long as you are able to make a mold, you can make a structure like that mold. So I see a picture of the B-2 stealth bomber that is predominantly made with composite material. Some of the unique features of that plane, including its ability to evade defense, were achieved thanks to composite material. So now, let me tell you about how these advantages of composites have helped the technology earn their way into a number of modern applications. Now, I'll start with the aerospace, defense, and space. So we'll talk more about this industry today. These are the industries where composites have really found a very fertile ground. And the reason is that all the advantages I described before, the ability to reduce weight, the resistance to corrosion, fatigue, tough environments, rapid changes in temperature, and the need for aerodynamic design really created a perfect opportunity for composites. So I'll talk a little bit later about the evolution of applications and how composites moved from making some secondary structures all the way to wings and fuselages of large commercial airplanes. But that's obviously the place where the advantages is. Composites are used in marine, America's Cup boats. Obviously, lightweight and stiffness are very important in these type of sports where it's really important to achieve the best performance. Likewise, talking about sport, motorsport, and luxury cars, supercars. Now, beyond the obvious advantages of composites like lightweight, when you look at this type of application in motorsport, there is one additional advantage of composites, that is the ability to absorb energy in a very controlled way and in a better way than metals. So when composites started to be used in Formula One, they significantly improved the safety of the pilot because of their ability to withstand a high-speed crash. Composites are used also in construction. Of course, I spoke before about reinforced concrete, but here I'm talking about fiber-reinforced plastics. You can make bridges with composite, again, because of the lightweight, the stiffness, and lack of corrosion. Sporting goods, bikes, hockey sticks, golf clubs. There are a lot of sporting goods where the ability to tailor the weight and the stiffness improves the handling of the bike or of the hockey stick, and therefore improve the performance. And one of the recent applications of composites is in shoes inserts. You might have heard that composites can help a runner in a marathon. And being a runner myself, I've seen the advantages that the composites can bring. Another example of application is in wind energy. Obviously, sustainable, clean energy that is being used more and more in the world. These blades need to be light, need to be stiff. Some of the offshore blades are extremely long and need very high stiffness. Again, that's another area where composites play a role. So what does a composite look like? So these are some optical micrographs of the cross-section of a composite materials. And specifically in this case, a carbon fiber composite. And I would like to highlight a few features about the composite. The first one is the layered structure. So you have multiple layers. These layers can range in thickness from 100 micron all the way to 200, 300 micron. You have fibers in multiple directions. So as you can see from the picture, there are fibers coming out of the screen, and there are fibers going transversally at 90-degree direction, and fiber going at an angle, plus minus 45. So that's what we call a quasi-isotropic layout. If you look at the two bottom pictures, and actually distinguish the resin that is what you see being dark, close to black in the picture, and the actual fibers. So, these are carbon fiber yarns that are made by thousands of individual filaments, each of which has a diameter of about 5 to 6 micron, depending on the fiber. So obviously a very, very unique material. Also when we look at its microstructure. But now let me share a couple of other reasons composites are unique. Reasons that are a bit less intuitive, maybe. The first reason is the way you manufacture parts with composites. So on the left-hand side of the slide, you can see one of the typical way of manufacturing parts with metal. Start with a big block of metal, and you machine a lot of metal away to make a part. Now, this is subtractive manufacturing, and typically when you use machining for metal, you are taking out up to 90% of the original material. So what our aerospace customer call buy to fly ratio is now very good. They buy a lot of metal, they can only use 10% of it in a part. Yes, there are other techniques to manufacture metal structures, such as forging or casting, but in general, metals are not manufactured through addition. Composites are. That's why I like to say that composites have been one of the very first examples of additive layer manufacturing. Now, I hope you can visualize this. I was hoping to show you a video, but I didn't trust the technology to do that. The way you are putting together composite structure is you are laying down multiple layers of material, fibers impregnated with resin, and I will talk a little bit more about the processes in a few minutes. And then once those layers are put together, the structure gets cured. So it goes into an oven or an autoclave, that is basically a pressurized oven. The pressure and temperature allow those layers to consolidate into what is ultimately an hardened structure. So the first uniqueness about composites is that you build the structure through additive manufacturing. Now, another uniqueness of composites is that I like to say you build the material as you build the part. This happens at the same time. If you think to the example I just gave, we start with material that is soft and sticky, and we are laying it down, putting it in an oven, and ultimately the material is built together with the part. There are not too many other examples where that happens. On top of that, there is a very intimate relationship between the design, the materials, and the manufacturing process. So you hear a lot talks about design for manufacturing. Time for manufacturing is extremely important for composite materials because of this reason. And it's also very important to have a clear understanding and dialogue between designers, material scientists, and manufacturing engineers. My experience, this is absolutely the best way to truly deliver the potential of composites, and not just mimic metals, but be able to design with the material and the process in mind. Now, GTMI is a manufacturing institute, so I absolutely want to talk about the manufacturing. So let me start with some very simple examples of how you manufacture composites, and then I'll deep dive a little bit. So there are many processes and variants of these processes that are used today to make composites. So now I'm going to cover all of them, but I will give you a bit of a high-level flavor of how composites manufacturing has evolved over the years. So early composites structures were manufactured using wet layup. It's a technique that today is still used to make certain structures like large boats. Now that's a pretty crude manufacturing technique. You have a bucket of resin, you have a dry fabric with fibers in it, you lay down the fabric, you try and hold it together, and then pour down the resin and use some tools to impregnate the resin. Then that structure gets cured. Now, what companies like Solvay do many years is take this process to the next step. The way we do that is we create and manufacture what is known as prepreg. So prepreg start for pre-impregnated material. So instead of bringing together the fiber and the resin right on the manufacturing site where the part is made, like people do with wet layup, we would provide already a pre-impregnated product like the one you see on the top of that picture, where the resin and the fiber have been brought together. And that product can then be laid down, typically by hand. Now, the next evolution of manufacturing is when you take that product and you slit that product to some precision width, and then do something else with that product in terms of tension control, release, and the likes, so that product can be laid out not by hand, but through the use of automated machines, like automated tape layers or automated fiber placement machine, like you see in that picture below. So again, this is a high-level summary of how structures can be made. Now let me go into a bit of a deeper dive. And in order to do this, I have chosen the industry where composites have found some very fertile ground, like I was sharing before, and that's the aerospace and defense industry. And I would like to use this picture of the history of fiber-reinforced plastics in aerospace and defense to make one very important point. Let me go through this history. At the top of this slide, you have materials. In the early days of composite in the 70s, fibers that were used were Kevlar, glass, not very well-known fiber called boron fibers. Then that fiber, the fiber evolution went to carbon fiber, standard modulus fibers. New resins were brought in, like epoxy resins. And then the technology kept evolving. The industry developed fiber with higher modulus. Companies like ourselves developed toughened epoxy resins that would allow us to have a resin with the ability to improve the damage tolerance, and chemistries that could enable higher temperature performance and better mechanical performance, like bismuth amide. So a lot of evolution on the material side. However, what was happening at the same time was a lot of evolution on the process side. So the industry evolved from crude processes like the wet layup and then the unlayup that I described before to automated process like automated tape laying and fiber placement, all the way to processes today where you can infuse the resin or you can cure a composite without any pressure. So you don't need any longer an autoclave. Now, the ability of materials and processes to evolve allow composites to gain more and more ground into applications. So this started with some secondary structures. So, in aerospace, we call secondary structures that are not essential to the safety of the plane. So you can lose that structure, the plane will continue to fly. So fairings, radomes, rudders, spoilers are examples of that. So we started with this. On the defense side, where there was a big drive for performance, composites went faster into primary structure. So they started with rudders, went into structures like stabilizers, all the way to wings and large structures, like the B-2 bomber that I showed you before, V-22 helicopters, all composites, and then all the way to more modern planes like the F-22 and the F-35. In commercial, it took a bit longer because of the size of the structures and because of the criticality of that structure. But today, you see composites being used in wings, fuselage, tail of a commercial plane. Now, I don't want to just give history lessons of the evolution of composites in aerospace and defense. The point I want to make in the slide is that it was not just material science that enabled composites to be used in all these applications. It was manufacturing as well. Had automated manufacturing not been developed, there would be no way to manufacture the wing of a twin-aisle plane or the fuselage of a twin-aisle plane by hand. It would be absolutely non-economic. So there is a very, very strong synergy between material science and manufacturing. And keep that point in mind as we go through the talk. So what's next? What's next for composites? I shared until now a bit of the history, the yesterday and the today. Tried to tell you a lot about potential and the advantages of composites. So what can happen next? Well, it is very clear, me and to the industry, that composites can be an absolute enabler for multiple frontiers of progress in multiple markets. Now take electric vehicles, cars, or even planes. Again, some of the advantages of composites, the ability to make very flexible type of shapes, the lightweight, the stiffness, are clear enabler for vehicles that need to carry a heavy battery and therefore need to be light. Hydrogen propulsion. There have been a lot of talks recently about hydrogen propulsion for both land vehicles and aerospace. Again, composites can really help. Consider a picture of solar propulsion. This is Solar Impulse that some of you may have seen. This was a project actually sponsored by Solvay that used our composite materials to make a solar power plane that did a world tour. Obviously, that was a prototype. Today, planes still fly on fossil fuel. They don't fly on hydrogen or solar energy. But we believe tomorrow composites will be an enabler. On the defense area, hypersonics. One of the new frontiers of warfare is hypersonic weapons. So weapons that can fly at 15, 20 times the speed of sound. Again, composites are big enablers in these areas because of their ability to control thermal management and the weight. Urban air mobility. We are evolving towards a future where people will be able to move in large metropolitan areas using the air and not using the ground. I live in Atlanta like many of you, and while these are slowed down a bit with the pandemic, you know better than me how tough it is to go from one spot to another in Atlanta. So urban air mobility is a great frontier, and composites again are an enabler for obvious reasons. Last but not least, talking about something that personally excites me a lot, space exploration. The United States has a very ambitious objective to get the first human on Mars in 2030. There are multiple technologies needed to make that happen, but clearly composites will be a big enabler. So, enabler from new frontier. What needs to happen to deliver that potential? So early in this presentation, I spoke about what I refer to as the traditional advantages of composites, right? Lightweight, lack of sensitivity to fatigue and corrosion, and so on and so forth. Now, I believe there are a number of other potential of composites that today are either not well understood or they are not well utilized. Maybe they are utilized in some industries, but they are not utilized in others. And I would put them in two buckets. The first bucket, I like to call it engineering freedom. And the second bucket, I call it integration in a very broad term. So when you look at engineering freedom, I spoke before about the shapes that cannot be made with metal. Let me give you an example where that advantage has been exploited. The wing of the 787 or the A350 plane. The number one reason that wing is made with composite is actually not weight, like most people may think. Weight, of course, is a big advantage in something that flies, but a very important reason is that it's not possible to make that aerodynamic profile that provides high fuel efficiency with metal, not in an economical way. Composites, you can make any shape you like. Multiple degrees of freedom. If you remember the picture where I showed you all the layers. Composites have many, many degrees of freedom. So if you just think about what you can change the type of fiber, and so its stiffness and its thermomechanical properties. We can change the resin. Within the composites, we can change the angle at which the fibers are oriented. We can play with a number of layers. So many, many, many degrees of freedom, including degrees of freedom that come from manufacturing once again. That allows to do what we refer to as advanced structural design. I really like this word, biomimetics, mimic natural structures. Remember what I said a few minutes ago, composites exist in nature. Evolution has brought very efficient structures like trees or like human beings with bones. And these are structures where the fibers are oriented in the direction of the load, and there is an intelligence in that design. So composites allow us to use that intelligence. Now, integration. There are a couple of ways to look at integration. One is manufacturing integration, and it's possible with composites to reduce a lot the power count. Again, if I show you an example where this has been already exploited, again, take the fuselage of a large commercial aircraft. If you have to make this fuselage with metals, you need a lot of parts that are all fastened together with rivets. If you make that with composite, you significantly reduce the part count because composites enable integration. You can bring together stiffeners and skin of a fuselage all at once without stiffeners. The other way to look at integration is about functioning. And again, think to the layer structure. Having a layer structure means that you can integrate certain functions. For example, electrical conductivity or the ability to store energy. That is what happens in a battery that, by the way, is a layer structure. Now, as I said before, some of this potential has been exploited, but I only believe that a very small part of that potential has been exploited today, and there is a lot more that can be done. So I want to talk to you about some of the opportunities and challenges that come with composites, and what I believe can be done in order to exploit these advantages. So we'll talk about the importance of simulation and modeling, talk about how a very trendy term, Industry 4.0, applies to composites, talk about another trendy word that is multifunctionality, again, how you can use composites to build intelligent structure. And last but not least, I shared about the importance of sustainability for Solvay. Composites have an interest dilemma on sustainability. They are a very good product to help sustainability because they are lightweight. So plane made in composites consumes a lot less fuel than a plane made with metal, and the same is true for a car. However, composites are not easy to recycle. So there is clear challenge and opportunity that we can exploit. So let me talk about those four areas. So let's start with simulation and modeling. I shared in the previous slide that the key advantage of composites is the multiple degrees of freedom. Right? Many layers, many different fibers. As a designer, you have all the freedom you need. However, of course, all these degrees of freedom create challenges as it pertains to designing a structure, analyzing a structure, and ultimately certifying a structure. That is a very important problem in aerospace where structure needs certification. Now, we're very lucky today. We're very lucky because computational power has really increased. And you've probably seen many of these charts that shows the evolution of computational power. Now, there is a clear belief we will surpass the power of a single human brain in 2025 and potentially hit a technological singularity and surpass all the human brain power, in the next 20 to 25 years. So we need to use this power. And being able to apply simulation and modeling, apply the advances in computational power to composites can create a huge value, because it can take that complexity and make sense of that complexity, and therefore fully allow us to use all the degrees of freedom. Now, the chart you see on the right is something we built together with one of our largest customers a few years ago. It shows what is known today as the certification pyramid in aerospace. Today, we do a lot of testing. In order for a structure to get on a plane, there is a significant amount of work that goes into breaking coupons, breaking components, breaking final structures, including a full wing. There is very little use of simulation. So again, using the science, the knowledge about composites, and combining it with computational power can allow us to really streamline that process. That means delivering better structures, delivering products to the market faster, and optimizing a lot faster than we do today. Now, let me talk about the multifunctionality. So I said before that with composites, you can use multiple functions and you can integrate. Now, when we look at the evolution of composites, yesterday, composite structures were what we would call monoskilled. Their job was to carry a load. Today, we are able to use composites with a number of enhanced physical, so thermal and mechanical properties that can reduce weight and avoid corrosion, etc. The big potential for tomorrow is to use composites to provide additional functionalities. And why is that important? Because the moment you are able to integrate multiple functions within the material and the structure, you are saving both weight and cost. There is less components to bring together, and there is overall a low weight. To give you some example, acoustic and vibrational damping. It is possible to introduce certain features within the composites that allow us to tailor the damping properties of the composites. Conductivity. Again, composites have had a weakness because they are not as conductive as metals. So one of the shortcomings has been that you need to protect composite from a lightning strike, and you also cannot do grounding and bonding of composites in a structure. Now, there are ways to bring conductivity into composites. Thermal insulation, excellent material to do that. Can you integrate more of that? Radar absorption, very important in defense. Technology has used one advantage of composites, that is you can change your curvature radius continuously. That helps, but there are other opportunities to influence that property. Structural health monitoring and the ability to treat a structure like a human being. If a structure is damaged, you are able to send a signal and you know that. Storing energy. And then last but not least, I couldn't do this talk without mentioning COVID once, antimicrobial properties. Obviously, that's something else that can be integrated in a structure and avoid additional cost or weight. So lots of opportunity in multifunction. Now, manufacturing. I absolutely believe, and so do the people who have used composites a lot, that composites can make processes simpler and can lower cost. Because you can integrate, because you need less expensive tooling and less expensive machines. However, today, a lot of people, especially those who are not familiar with composites, have a perception that composites manufacturing is not a science and requires a lot of brute force. Now, that's true in a lot of cases, and it doesn't need to be that way. Again, there are a number of technologies that can help fully exploit composites. Advanced process monitoring, statistical process control, not to mention artificial intelligence and machine learning. You can just think, again, to everything I said before and the inherent complexity of composites and manufacturing. The use of artificial intelligence and machine learning can help improve the design, the quality, productivity, and even the supply chain. So lots of opportunities. Sustainability. So I shared before the paradox of composites. Lightweight, you consume less fuel, so very sustainable technology. However, today it's very hard to recycle composites, and composites are by and large still derived from oil. So what are the opportunities there? You look at carbon fibers. There are opportunities to manufacture carbon fiber using sustainably derived acrylonitrile, that is a key ingredient or the precursor of carbon fibers. Now, we worked on a project with the Department of Energy to make acrylonitrile from biomass. Carbon fiber production requires lots of energy because you need to take fibers and you need to heat them at very high temperature for a very long time. How can we do that with low energy? Resins. Can we look at having monomers that are derived in a sustainable way? Recycling. Again, today, especially with thermoset composites, there are only very crude and inelegant ways of recycling composites. A thermoset, by definition, is set, so it's not easy to go back to the original component. So what people do today is they will burn the thermoset, use a pyrolysis process, and then recycle what's left. Not very elegant, not very efficient. And then, last but not least, there are opportunities to create product forms that can come from recycling or can come from sustainable products in order to use them for certain applications. And we have examples where we have done that. You can also think about turning some of the waste streams from this industry or from other industry into building blocks. So lots of opportunities. Now let me conclude, and I want to conclude this talk talking about talent, talking about people. One of my mentors once told me, everything you will see in life is about people. So let's talk about what can talent do in this field. So I hope to have convinced you by now that composites have a huge and very exciting potential. And this is a potential that today is sometimes feared. And I believe this potential can be embraced. Don't be afraid of multiple degrees of freedom creating complexity. Use that. Don't be afraid that manufacturing it's not as efficient as it could be. Leverage that. And the way to do that is very simply multidisciplinary expertise. The future of a technology like composites goes beyond chemistry and engineering. As you have seen this presentation, you probably notice how many sciences and disciplines can be of help to composite: digital, computational science, physics. I really believe that most, if not everything, of what you are studying today is relevant to composites. And so, to conclude, I put some pictures here to tell you a bit of the story I wanted to cover in this talk. Now, we started with a picture of the physics conference, the great scientists that made possible a lot of the progress that we have today in the last century. Spoke about the evolution of composites, and I have at the bottom a picture of my children in front that was taken a few years ago in front of an F-35. It is an all-composites plane made with a Solvay material. I absolutely believe in the need to inspire young generation about science and technology. Very importantly, about the ability of science and technology to achieve progress for all of us and for humanity as a whole. This is what the founder of Solvay believed in. This is what I personally believe in. So for me today, it's a real pleasure to talk to an academic institution like Georgia Tech and to have the honor to have all of you listening to this, because I hope that you can take something from this and use it to be inspired and to inspire the new generation of scientists and technologists, because there is a lot that can be done. Composites is a great area for that, but we definitely need a lot more of that. And with this, I'd like to conclude and go to Q&A. Thank you.
Thank you, Dr. LaFaro, for a truly inspiring lecture. We appreciate your time today, and we appreciate the attendees who have logged in today. And it looks like we've received a number of questions. The first question I will address, and the other questions I will relay to Dr. LaFaro. The first question is whether a copy of the slides from the presentation will be available. And a recording of the lecture will be posted within a few days on the Georgia Tech Manufacturing Institute website past lectures page. And I've added the URL in the Q&A panel as well as event chat. But for reference, the URL is www.manufacturing.edu/lectures. So please take a look at the website within a few days. You can also find a listing of upcoming events and lectures that GTMI will be hosting in the near future. The second question is for our speaker here. Thank you for a great lecture. Can you comment on the role of nanomaterials may play in future composite materials?
Yes, I can. No, we spend a lot of time and thinking about nanotechnologies. Nanotechnologies have absolutely a place in composite materials technology. There are some technologies that we are using today, and there is a lot of potential that can come in the area of multifunctionality. If you take, for example, Bucky paper, that has a great potential to tailor both mechanical and thermal properties. What is important for me about nanotechnology is there's been a lot of hype about the nano in the previous years, and like every technology, in my experience, follow what's commonly known as the Gartner hype curve. They are very excited, and you overestimate the benefit. So you go into a bit of a depression and then eventually figure out how to leverage it. I think nanotechnology today is in a place where we have gone past the hype and we can really use it more and more. But I absolutely believe it is an enabler, particularly as it pertains to the area of multifunctionality.
Thank you, Dr. Faro. And the next question is regarding inspection and modeling technology. The question is, can you share your view as to why composite inspection and modeling technology continues to lag behind advancements of related material development?
Well, I'll start by saying that unfortunately I have to agree that it continues to lag behind. Now, why it lags behind? I think one simple reason is age. Again, the title of this talk was Young Technology. Composites have not been around for as long as metals. And I believe that's the reason we don't have the same advanced techniques. I think the second reason is really around the theme I was trying to cover today, is that there has been a lack of ability to bring multiple science together. Again, because composites are so new, they require a lot of combined expertise. Because composites are at the crossroads of material design and manufacturing processes and have this inherent complexity, they require multiple disciplines. So I think what we have struggled with is seeing that happen. See people, see chemists come together with engineers, come together with manufacturing people, and then more importantly, see people who can speak the multiple languages of science and technology and are able to advance the progress. So in short, I don't believe the reason is due to some kind of flow, technological flow, is really down to talent once again.
Thank you. We have a couple of more questions to address. The first is, how can the future of composites move towards universal standards to reduce overall cost rather than proprietary materials standards qualifications set by OEMs, especially in the aerospace industry? While most OEMs do not seem willing to change at this time, MROs and end users need this.
Yeah, this is a great question. Again, one is I believe that we will see more of that standardization. We saw that happening in metals before, and that's just been the history of even advanced metal like titanium, where today there are a lot more standards. Same for aluminum. I believe we will see that for composites. There are a number of initiatives in the US and other countries that are trying to do that. The one example is the NCAMP database that is supported by NIAR in Wichita. So there are clear pushes in this direction. What is important for me is that the push toward standardization doesn't equate to lose all the degrees of freedom of composites. So I would like to have my cake and eat it. I would like to be able to standardize more because I'm sure that will enable broader adoption of composites. But I would like to do that without losing some of these very specific advantages of composites and the ability to use all those degrees of freedom. And this is where I believe the industry needs to evolve, that the competitive advantages of OEMs in the future is not necessarily just having a material database, but it's a lot more about being able to exploit the complexity of that material database in design, in manufacturing, and in the application of the material to meet some mission requirements. So I think we will see this natural evolution.
Terrific, very interesting. And next question is, what is the newest and most recently discovered composite that has major potential?
I would say, I don't want to pick just one material, but the way I would like to answer this question is there isn't one. There is, I actually don't believe, having been in composites for a while, that there is a silver bullet solution or a great solution to every challenge. I believe I believe in a mantra that is the right material and the right process for the right application. So the way I would answer that question is that we have seen advances, composites for manufacturing. What I mean by that is composite materials that enable new manufacturing technologies. So we'll give a couple of three examples that are near and dear to my heart. One is resin infusion. The ability to infuse a structure can improve integration, can improve the ability to make certain shapes. The Safran and GE have been able to make the fan blades of the LEAP engine using a resin transfer molding technology. And this has been a huge breakthrough because those blades have been made with metal since the start of the jet age. Thermoplastic composites. So a lot of the composites you see around today have a thermoset matrix. Thermoplastic composites have the potential to enable new processes like press forming or continuous compression molding. And they also give us maybe a better chance at recycling. Curing out of an autoclave with just vacuum and being able to do that in a press are also new materials that enable new processes. So I don't believe, I don't want to pick one technology. I think there are multiple advances. And the key point there is those multiple advances are not purely driven or enabled by material science. They are driven and enabled by the confluence of material science, manufacturing, and an understanding of the mission requirements.
Thank you. And the questions continue to stream in. This is a very intriguing talk. So the next question is, with government-sponsored World War II efforts advancing many DoD manufacturers' understanding of metal materials for aerospace and defense being such a significant advancement for manufacturing in the 1900s, do you see any hurdles related to the proprietary nature of composites being overcome in the near future?
I think it's a similar question to the one I answered before about standardization. And so maybe rather than repeating the answer, I will give a little bit more color and expand on it. I do believe and would like manufacturing to be sexy today, if I haven't made it clear enough in this talk, and really highlight the importance of manufacturing. I believe that government, academia, and industry should and must work together in order to advance manufacturing of the type of structures that can be made with composite materials. And yes, once again, I believe that as we progress, what is today's competitive advantage, that is the proprietary formulation of a composite or a proprietary database, will become something we take for granted. And there will be new competitive advantages that come in the area of digital, in the area of being able to simulate, and in the development of new manufacturing processes. So I don't believe we need to see how things will progress going forward. Or what's definitely needed is the ability to bring a few minds together and lay down a roadmap that helps us to do things in the right sequence. And that's again where academia and government are essential. Industry alone will not be able to do it.
Thank you. It looks like we have 2 more questions remaining right now. The next is, what are the biggest hypersonic composite challenges that you see that we need to overcome in the next 5 to 10 years?
Yeah, that's a great question. I would say it's all down to manufacturing. I believe that we can have, we will reach the performance requirement, and in many cases we reach performance requirements today. I think the key nut to crack is the ability to manufacture structure at rate, to manufacture structure in a controllable way, understanding well the relationship between the inputs and the outputs in the process. You know, today, some of the components being made are being made with medieval processes, and we can do a lot better. We can absolutely do a lot better. So the simple answer to that question is it's again around manufacturing being the biggest challenge. I don't want to suggest that there are no performance hurdles in front of us. There are, but I believe we will overcome these hurdles. We understand structure properties relationship, and we know how to formulate for effects. What will be the biggest hurdle is the product.
Thank you. And the next question is regarding modeling and simulation. That we noticed there are some significant advancements in modeling and simulation of composites and their manufacturing processes. However, a lot of applications still rely on experiments. What do you think are the developments and needs combining both modeling and experiments in the future?
Yeah, it's a very broad question. Listen, I think we need both. I don't believe for a second that we can just use modeling. No. Today, if I give you a crude example, when I look at something that is purely modeled and doesn't get tested, the only example I can come up with is nuclear weapons. Nuclear weapons were extensively tested back in the 60s and 70s. You absolutely need experimentation, and you need to gather data, but you need to do that using science to make sense of the data. What I believe we do today is we often hide behind statistics. So if you look at what we do to certify material, we do an enormous amount of testing and break thousands of coupons. And it is really hiding behind statistics or using statistics to provide confidence. And okay, statistics can provide confidence, but I also believe in the power of science to provide confidence. So ultimately, we need to break coupons. We need to simulate. We need to build the Y as a function of X that links inputs with outputs. It sounds very simple the way I say that. It's not that simple, but I absolutely believe that in this century that's possible.
Thank you. And just a few more questions if you have a few more minutes, Dr. Lafaro.
Sure.
The next is, how does the general fatigue performance of fiber-reinforced plastics compare to that of metals? Specifically, can composites be manufactured so they achieve an endurance limit?
Yeah, fatigue is a very interesting topic. I did say before that composites are virtually insensitive to fatigue, and that is true within the range of deformations that composites are typically used in. There are composites and metals fail in very different ways, right? Metals fail through fatigue crack growth. Composites don't. The inherent nature of composites means that you have a number of crack stoppers, if you will, within the structure of the composites. Now, composites have other challenges that we have worked over the year to address, such as the lamination and out-of-plane performance. But fatigue is not a challenge with composites, and this is why the composites are used in a lot of applications that are fatigue sensitive. Now, this is why composites today allow a fuselage to be pressurized at a lower level, because at a lower altitude, and therefore improve the comfort of passengers, because the process of blowing and unblowing a balloon that is a fuselage through pressurization is very intensive, and composite can tolerate that. So I actually do believe composites have an inherent advantage over metal. I would not say they are totally fatigue-proof, but I would say they are a lot better.
Thank you, Dr. LaFaro. And it looks like we've reached the end of our time slot for this lecture. Thank you very much for a fascinating lecture. And thank you to our audience members for joining us today. As mentioned, we will post a recording of this lecture on the GTMI website, so please take a look there, where you can also see a list of other upcoming lectures and events hosted by GTMI. Have a wonderful afternoon, everyone. Thank you.